Our last topic in this section is about infinite series and partial sums, which will actually be extremely important to us because infinite series are what we're going to spend the vast majority of our time on in chapters 10 and 11. So infinite series are series that add up to infinity, amazingly enough. So you just keep adding and adding and adding. And I should make a note right now that that symbol is the Greek letter sigma. It means to sum, which we've seen in Calc 1, of course. It's sigma, S-I-G-M-A. We saw it in Calc 1 with Riemann sums, for example, but just a little reminder that that's what that is, right? So it means we add. Now, an infinite series will add up forever. You just keep adding and adding and adding and adding. A finite series will add to a finite number, right? You can see up there that we have a finite number of 5, for example. All right, but there's a little bit more going on that we kind of want to denote. Oh, and before I go any further, just really quickly, this notation denotes any series, whether a series of positive terms, negative terms, alternating terms. It's just a fast way to write series. It's the lazy man's way, lazy person's way to write a note or to write a series. And I will use it regularly. All right. We want to look at this whole adding to infinity thing just a little bit more finely. And this is a very illustrative example. So we have a unit circle. Unit, actually it's unit square, sorry. Unit square because the sides are equal to 1 and the area is equal to 1. You can see it. And we are going to subdivide that region. We're going to cut it in half, then cut what remains in half, right? So we cut the square in half, right? There's the shaded part. Then we take this white rectangle and we cut that in half, which gets us to this piece. Then we have this little white square right here, and we cut that in half, which gets us to there. And then we cut that in half, and so on, and so on, and so on, and so on. And you can actually see right here, it's telling us what the sequence is. That the sequence that builds this is 1 over 2 to the n, right? 1 over 2 to the 1 gets you the first one. Then 1 over 2 to the 2 is a fourth. 1 over 2 to the 3 is an eighth. 1 over 2 to the 4 is a 16th, and so on. So we can see that sequence that's building is, right? So first question is saying, how do the sequences relate to the partial sums? Well, the sequences help us build these sums, these series values. So part 1, the sequence, which was a sub n equals 1 over 2 to the n, which is an explicit formula, helps us build the series, right? All right, now let's look at those partial sums in series a little bit. So if we look at the first one, S sub 1 is saying, hey, start at n equals 1, but end at n equals 1 for that sequence, 1 over 2 to the n. And what would you have? Well, you'd have a half, right there, half. What about this one? S sub 2. So add up only the first two. Sum the first two. That's right. It's called a partial sum. So you're adding part of that series up. So S sub 2 would be, okay, take this series, but only add the first two, right? Part of it. And then it's still that sequence, 1 over 2 to the n. See what I mean now about it helps us build that series? And a half plus a fourth is 3/4, or 0.75. And you can see it, right? 3 of the 4 fourths are shaded, right? If you divide it in half and then in half, 1/4 is unshaded. All right, S sub 3, you're going to add up the first 3. So you're going to take this infinite series, starts at 1, but you're only going to add up the first 3 parts of it, right? Hence the partial sum. And what will it be? It would be a half plus a fourth plus an eighth, which is 7/8, or 0.875. And there seems to be a relationship going on here, right? Let's do it one more time. S sub 4 would be a half plus a fourth plus an eighth plus a 16th. It's from 1 until 4 of that original sequence, which is equal to 15 over 16, which is 0.9375. So I've added up the first 4 terms. I've added up part of that sum. Now S sub n would be adding up n terms, right? It's a partial sum, right? You're adding up part of it to n, right? As opposed to the infinite series, which would be adding up to infinity. Now, there's a new sequence getting built. Can you see it? Let's take these numbers, a half, 3/4, 7/8, and 15/16. They're developing a new sequence, so that's part 2. So there's a new sequence of those partial sums. And that sequence, which we'll call S sub n, is equal to a half, 3/4, 7/8, 15/16, and so on. All right, what is that as an explicit formula? Well, the denominator is pretty easy to see because it's the same as it was for the original fraction, right? 2, 4, 8, 16. So that's 2 to the n. But did you catch what always is happening? I mean, it's easy to see. I don't know. I think it's easy to see over here. There are 8 eighths, 7 of which are shaded. There are 16 little subsections here, 15 of which are shaded. It's always the number in the denominator, take away 1. 8 take away 1 is 7. 4 take away 1 is 3. 16 take away 1 is 15. So if I take that number in the denominator, which was 2 to the n, and I take away 1, lo and behold, I have a new sequence that's built called the sequence of partial sums. Right there. Oop, my n got weird there. There you go. So I built my sequence into a series, right, which is where the 1 over 2 to the n is coming in. That's the explicit formula, but then I'm adding those up. And as I add piece after piece after piece after piece, I can see that I've built a new sequence, but it's the sequence of those sums. And now there's more. I want to make a conjecture. What's going to happen if I go to infinity of my sequence? If I take a sub n, right, which is what we're doing. So we take our little a sub n sequence and we add up to forever. That would be the limit as n goes to infinity of that new sequence of partial sums, wouldn't it? Right? So if I take this little pink sequence and I just keep adding and adding and adding and adding, which is what all these additions are, then that's really taking the limit as n goes to infinity of this sequence of partial sums. Where are we going to? Which is equal to the limit as n goes to infinity of that new formula I came up with, 2 to the n minus 1 over 2 to the n. Where do you think that's going? Look at these squares. Where is this heading to? I'm going to put a box around this conjecture because it's very big and important. It's heading to 1. Check it out, right? You can add to forever and be going to 1. Let me prove it to you. Okay, so let me go to Desmos. Well, proving is a strain a little bit. It's more that I'm showing that this works numerically. I'm kind of waving my hands out a little bit. All right, so there was the sequence, a half, a fourth, an eighth, and so on. There's the new partial sums. See it right here? Where I'm adding up, right? I'm adding 2 to the n, I call it n6 minus 1 over 2 to the n6. So as a half, 3/4, which is 0.75, 7/8, which is 0.875, and so on and so on and so on. And I can keep going, right? I can go 7, 8, 9, 10, 11, 12, how about 100? Hey, look right there. It's heading to 1, right? It's actually heading to 1 so much that Desmos doesn't even handle decimal places anymore. Amazing, isn't it? So those partial sums add up. And if you make it an infinite series, it's adding up, which means that we can sum to infinity and still get a number. And if that's sounding familiar to you, that's because in section 8.9, when we did improper integrals, right? When integrals went to infinity and we were able to find the area under the curve and it still went to a number. It was called something. Oops. I'm running out of space over there and I want to fit this in. There we go. There's a definition that we learned in section 8.9 for that. It's called convergent. Right? It's possible that the sum will converge. It's also possible it will diverge. And that's where we'll be spending a lot of our time in chapter 10 to figure out whether it's convergent to a number or it diverges. Right? Not this particular problem. This problem was convergent. It was convergent to 1, and we proved that.